2024. But before I start, I would like to start by acknowledging of the country. On behalf of PIANC Australia and New Zealand, I would like to acknowledge the traditional custodians of the country throughout Australia, including the land on which we gather and meet today, and recognizes their continuing connection to land, water, and community. We do pay our respect to them and their cultures, particularly to elders past, present, and emerging. Getting back to the technical presentation, this is one of the fantastic publication recently published by PIANC. If you guys are aware of, previous PIANC MarCom publication as part of Working Group 33, published in 2002. Since then, a comprehensive overhaul, has been happened, and I'm sure Harvinder will go through that one, and I'm not going to provide more details in that respect. But PIANC, what is PIANC? PIANC, Permanent International Association of Navigational Congress. This is how the acronym stands for. After a few years, changed the name to World Association for Waterborne Transport Infrastructure. So, but still, kept the PIANC acronyms at the beginning, and sometimes, that's give us a confusion. And I was asked several times, what's the alignment between PIANC and current name of the association, and that's the reason I try to describe every time I am briefing about the PIANC. So what is PIANC? The main aim and objectives of PIANC is to enhance the navigational function of waterways, ports, and coastal zones. And we are trying to achieve sustainable development through balancing the environment and also economic interest at the same time. And given that, in Queensland, as one of the states in Australia, probably you guys might be aware, we got the longest coastlines, among other states, including the islands and, the other small islands offshore and onshore. And so this is one of the things that I believe, Queensland is one of the best, place to deal with the waterborne infrastructure. And this is how the PIANC Northern chapter is working. The second aim of the PIANC is to improve the planning, design, construction, management, operation, and maintenance of inland waterways, both in sea and inland ports, also including their facilities and their connection to the hinterland. Also, we are trying to contribute significantly to the integrated management of water systems. And also we are trying to promote the optimum use of the economic resources for the construction and operation of ports, waterways, infrastructure, and whatever facilities are related to these infrastructure. It is very important to communicate effectively the advantages of waterborne transport infrastructure, and this is how PIANC tries to facilitate that sort of communication. We are trying also to enhance services to all members, and also we are trying to promote the exchange of technical and practical experience, including cooperation with sister associations who are working, directly or indirectly in waterborne transport infrastructure. As you have seen, and as you can see in our technical event, we are going to talk with one of the recent publications. And I want to highlight, this is the core of the PIANC. We are trying to develop and contribute to high quality technical reports. And these technical reports being developed by international community working groups. And we are trying to significantly participate in that one. And I can say within Australia, we have a very strong nominees in that working groups. Comparing worldwide. Networking is another way that we are trying to share our knowledge and exchange our experiences. And in order to maintain the high quality of technical contributions, paying attention to young professionals is very important to us, and that's the reason we have a board member assigned to develop the facilities and trainings and mentoring for young professionals, and we are always encouraging young professionals to get into that industry. Globally, if you want to know, we got 43 qualified members, and but only 27 of that qualified members, they are national qualified members or national section. And PIANC Australia and New Zealand is one of the strong national sections across the world. There are 1,800 individuals, including 1,800 individuals, as well as 500 corporate members, including port authorities, professional associations, universities, public and private sectors. Within Australia and New Zealand, we have more than 200 individual members, 50 students, 95 corporate members, and I believe that corporate members rise above 100 by now, and they are from public, government, technical institute, consultant engineers, contractors, and suppliers. So we got a variety of corporate members involved in our corporate membership system. In terms of the contribution nationally, we are running two major biennial events. The PIANC APAC is one of them, and also coast and ports is another one. For the coast and ports, we have a joint organization with PIANC Australia and New Zealand, and also the Engineers Australia. So we are 50-50% helping each other to have that coast and ports. And the last one happened last year in Sunshine Coast, and it was one of the big events. In terms of the APAC, the next one is coming up next month, 27th to 30th August 2024 in Sydney, and it has been well received. We already have more than 250 attendees, and we accepted more than 110 papers. So that's the record breaking since we started PIANC APAC in 2020 in Australia. So as you can see, in order to provide technical insight, PIANC has 4 commissions: MarCom, Navicom, and also the other NVCom and recreational commission. So these are 4 commissions that technically work and deal with the technical guidelines and reports. So given that, Northern chapter is one of the regional chapters. We have more than 13 leadership in our committee members, and it is well structured. We have a treasurer, we have a secretary, we have a young professional rep, and followed by a variety of the members from different consultant engineer and also port sectors. We are one of the biggest regional chapter in terms of number of events that we organize, and in terms of the collaboration. And we are pretty glad that we already organized several events. And as you can see in my slide, every month at least we organize one event, and for the remaining month of the year we also have planned and fixed events to be held. That's regarding our events. I want to just get back to the PIANC APAC 2024. that's going to happen in August in Sydney. And if you haven't registered yet, I do recommend you guys to register, as I believe by this morning, as I talked to the organizing committee, I'm part of the local organizing committee for that one, and I'm chairing the technical part of that conference as well. But the number of remaining seats are pretty limited. If you are keen to get there, I do recommend to do your registration at least by mid of next week, as I believe they are going to close the registration very soon, because we don't have the capacity in our auditorium. The opening session doesn't have that capacity to to accommodate more than 70 people. So that's one of the things. It's good to register as soon as possible if you're interested to attend. That's all. I'm not going to take your time more. I would like to thank Jacobs and also local organizing committee, Harry, and also other people from Jacobs. And also I would like to thank Harvinder for accepting to provide such an insight, as I believe he was one of the active working group member, and I'm sure he has something to tell everybody, and we are going to learn from him. So we can't wait to see what Harvinder is going to say. So back to you, Harry. Thank you very much.
Thanks, Sam. We have some brochures also of PIANC Australia New Zealand on your desks. So if you're not members of PIANC yet, you have some information there. So you can feel free to join the PIANC. Okay. So now I ask Josh to provide a welcome note on behalf of Jacobs.
Yeah, thanks, Harry. Thanks, Harvinder. Welcome everyone in person to Jacobs here in Brisbane, and welcome to everyone online. My name is Josh Abrahams, Maritime Structural Engineer in our Brisbane team here. I won't take up too much time because I know Harvinder's got a good presentation, but just to give a bit of a brief overview of Jacobs and our capabilities globally in the maritime business. So globally, we have the industry's largest ports and maritime team. Across the globe, we have over 700 ports and maritime specialists. So on the map there in the blue circles, we have our staff numbers, and in the green dots showing our projects and offices. Over 150 years worth of experience, largely through our legacy company Helcro. And as of 2023, we're ranked in the top 2 ports and maritime service providers in the ENR rankings. So some of the services we provide to our clients, quite a range across the ports and maritime market, from dry bulk projects, container terminals, port facilities, general maritime infrastructure, as well as specialised infrastructure. In addition to these, we have a range of services that we provide our clients in various types of projects, whether that be conventional design, as well as construction management, planning and approvals, modelling studies. There's a lot of points up there. I won't go into all of them, but we cover the market quite well. So focusing on our ANZ capability now. We have about 20 dedicated maritime team members. They're largely spread across Brisbane, Sydney, Melbourne and Adelaide. And I guess our key skills here are providing maritime structural engineering, port planning and logistics, as well as coastal modelling and engineering. But in addition to those key team members, we've got a bunch of other support team members across those offices I mentioned, as well as in Darwin, Perth, and over in New Zealand as well. So, keen to catch up with people here in the office after the presentation, but I'll hand over to Harvinder because he's pretty keen to talk about fenders.
Thank you, Josh. All right, my name is Harvinder Singh, and for those of you who don't know me, I sat on the PIANC Working Group 211 committee, and I was part of the committee that represented ANZ to PIANC International. So there were two of us from Australia, myself and Bob Lamont-Smith, who's based in WA. So I've prepared a set of slides today, and I thought I'll start off by talking about my experience and my insights that I acquired from the working group itself, then moving across to what's latest in the 2024 Fender guidelines. And then the key thing that changed is berthing velocity and partial energy factor. So these are two main design aspects that has changed and evolved from 33 to 211. I'll also jump into a bit of fender system selection, and then we'll go into the hull. Hull pressure hasn't changed a lot, but we've learned quite a lot in the process of putting this guideline together. Then I've got a good, interesting slide down there which talks about differences in fender sizing. So what I've done is I've taken an example. I've designed it to 33 and designed it to 211, and I'll show everyone what the difference are and what happened when we use 211. And then we'll talk about my favorite section, testing of fenders, if there's extra time at the end of it, and then we'll open the floor for discussion. Right, now how I benefited.
The attendees to have the questions towards the end. Those who are online also, if you can keep your questions towards the end, but you can send the questions in the chat window, so,
yes,
but it will be answered towards the end. Thank you.
Yep, for those who didn't get that, please keep your questions till the end, and I'll finish mine, and then you can shoot your questions online or in person to Harry, and we'll get that answered. Now, sitting on the working group was pretty exciting. It was pretty scary for me because this was the first working group I ever got into, but I actually enjoyed it at the end of it. There was a lot of hard work. I met a lot of new people, networked with a lot of professional globalies. I call them fender junkies like myself. And then I also obviously had the chance to mingle around port authorities, manufacturers, engineers, naval architects, captains, shipbuilders, and a lot of people in that likes within the marine world. So it was a pretty good experience for myself. It was a big learning curve for myself as well. So besides that, I understood the complexities in group dynamics, decision making. A manufacturer looks at the whole thing in a very different lens, and an engineer looks at it at a different lens. A port authority looks at it at a different lens. So what we've done is we've taken the learning of everything and put into perspective into this guideline. So this guidelines not only caters for engineers, but it caters for manufacturers, it caters for end users, it caters for everything. We cover everything from the planning aspect of a fender system right to removing it. What do we do when we remove it? Do we recycle? Do we throw it away? How do we dispose it safely? So things like that is covered in these guidelines. Now, travel is my favorite thing to do when I'm not at work. So I got a chance to travel quite significantly with this. I think there were 3 trips to Europe and 2 to Southeast Asia, and I've met a lot of new friends on the way. So I've learned a lot about regional diversity. Now, how I contributed is I used my diverse perspective of being an engineer, the lens that I look at how design of fenders are done, and I've inputted it a lot into these guidelines. It's not only me, there's a lot of other engineers as well who's involved in the whole thing. So I've also expressed a lot of views from the ANZ region before I dashed out in this fender venture, this working group. I did reach out to a lot of engineering houses within ANZ to get their views, their opinions, and what needed to be changed. I did reach out to quite a few people here as well. So that's what I've populated and taken up to the working group to be addressed. I'm just going to quickly jump to the next slide. Now, the reason for me to put this out there is I'm encouraging a lot of people, whether you are a young engineer, old engineer, experienced, unexperienced, the minute you see a call for a working group opened by PIANC ANZ, please, if it's within your niche area, you're confident enough, you've got the experience, put your hands up, send an email to PIANC. A couple of working groups are still open for grabs. please put a hand up. It's a fantastic experience. So that's why I wanted to share my insights into the working group itself. Now, who is the build of PIANC working group? There's a couple of big companies out here globally at different regions, different landscapes. They're manufacturers, they're engineering houses, they are end users, they are ExxonMobil who represented OCIMF to the working group. So there's a representation from the wider industry into this. Now I just want to make a point here. It is not these companies only that pull the working group together. There was a lot of collaboration of other engineering houses around that came. So it's an industry-wide effort, but not so much of what we've got in here. Now, I couldn't resist but to put this slide up. The picture on top is a group of us gathered in Port of Doha. That was before COVID. And then the picture in the middle was during COVID. And the picture right at the bottom was taken at Shibata Fender facility in Hamburg, Germany. So the duration of the working group was meant to be around 3.5 to 4 years. Now, due to COVID, which nobody expected, it went on to 5 years. But nevertheless, we still made it towards the end and got this document compiled. A bit of background on fender design guidelines. I've captured a document that was published in 1984, 40 years ago. And this guideline, this Bulletin 45 was what designers used as their go-to design document. And then in 2002, I think most of us here in the room is familiar with Working Group 33. Working Group 33 lasted for 22 years, and this guideline was actually put into practice still until present day. Now, the new guideline, which is MarCom Working Group 211, was released in March this year. And there is a transitional period of 2 years between 33 to 211. So in March 2026, Working Group 33 would be totally obsolete, and all designers need to pick up the new working group to start off with their technical work. Now, the latest fender guidelines for PIANC. Now, Working Group 211 is not just an update, it's an overhaul of the entire document. I think some of you must have read it or must have seen it here, or most of you must have read it and seen it. It's totally different to what Working Group 33 is. So I just want to make that very clear on here. Now, 211 described physical process of berthing better than 33. It's not descriptive, but it's more probabilistic. I'll explain that a lot further in the slide. Now, it has higher velocities, but I'm going to put a caveat there. It has higher velocities when you don't have site data. When you have site data, the design changes, and I'll go to a bit more in detail later after this. Now, it has lower berthing angles. It also includes multiple fender contact, which 33 don't cover. So putting that into perspective, 211 is considered to be more safer in the overall system design itself, because it caters for a very bespoke condition rather than a prescriptive condition in 33. Now, 211 strongly recommends site-specific information, as I said. And then if local knowledge is ignored, fenders might be over-designed. So what we are emphasizing here is data collection on site. So velocity is very, very important to fender design, and that is a key to the new guideline. I think everybody here would be familiar, and online would be very familiar with this. Mr. Brolsma created these curves in 1977, coincidentally the year I was born. So I was not there to witness that, but we did use it a lot in our design work previously. So Working Group 33 berthing velocities curves were derived assuming 100 berthing per year. So the figure on your right is an abstract taken from Mr. Brolsma's paper published at the PIANC World Congress in 1977. So with that curves, the Brolsma curves was produced, which you see with A, B, C, and D. So this is what most of the industry is used to, and we've been using this for quite a number of years. Now, it's very important to understand what Working Group 145, which is berthing velocity analysis, has done, because 145 was published a lot earlier than 211. So it was key that we abstract whatever learnings we got from 145 into 211. Now, historical data suggesting a correlation between berthing velocities and vessel sizes can't be confirmed. Right? That's one thing is noted in our 145. Therefore, applying this velocities curve to large sea-going vessels may pose a safety risk. There's also no evidence that berthing velocity is directly influenced by the type of marine structure, whether it's a flexible structure or it's a rigid structure. Regardless, the type of fender system, UKC, it doesn't affect the system design itself. There's no evidence of berthing velocity directly influenced by, sorry, I'm reading the line again, but no direct correlation between environmental factors. Sorry, somebody's trying to get me online. But so no direct correlation between environmental factors was found in Working Group 145. Berthing velocity strongly depend on berthing procedures in place. Now, operational conditions is key with the 145, and that's what influenced the velocity of the vessel coming into the berth. So this was the findings in Working Group 145, which Working Group 211 incorporated. So what's changed in the berthing velocity? So 211 uses local site-specific information. The berthing speed limits, use berthing speed limits, if any. So whatever berthing velocities collected within a port or a regional area can be applied to the structure which we are looking to design. Now, statistically examined berthing records, probability of accidents is 0.02. Now, that graph there was plotted out by one of my colleagues in Working Group 211 to determine where the niche area of the probability of accidents for berthing velocity. So all the factors used in the 211 is based on this probability of accidents. And when no information is available, designers can use this table, which is in, I think, 5.3 on the document, where the velocities are slightly conservative, but applicable for the type of vessel and type of condition. Now, you will also note favorable, moderate, and unfavorable. Now, there is condition given for these three categories in the guidelines, which advises a designer on under what circumstances favorable is used, moderate is used, and unfavorable is used. Now, this is only to be used when we don't have any data available for a specific site. So in conclusion, 211 describes the berthing process of a large vessel more accurate than Working Group 33. Now, correct usage of 211 will provide a berth with optimal fenders, often slightly more economical than Working Group 33. Correct use means using as much local data and experience as possible. The designer should also always talk with potential users like masters, pilots, port harbors, if present. So in a nutshell, the velocities in 211 is a lot higher if compared with the Brolsma curves. But the advice from 211 is to go back to site-specific data. And if site-specific data is not present, that's when we fall back to 211. Next thing on today's talk is about partial energy factor. Now, I think most of us online and here, we are familiar with this table over here, which is abstracted from Working Group 33. So this is quite deterministic. So we just pick the type of container, type of vessel, and we pick the berth impact. And sorry, it's probably a typo in there. And we determine what the abnormal factor is, and we apply it to our berthing energy. But that's not the way we handle it in our 211. Now, the effect of fender failure on a berth operation is not included in the factor of safety. It's unknown. The frequency of berthing is not considered in the factors of safety in 33. Sensitivity of the structure supporting the fenders is also not known. It's unrelated to the factor of safety. So what I'm trying to put perspective into this slide here is there's no relationship between all these criteria, abnormal berthing, there's no relationship between all these factors to the factor of safety used in working group 33. So in short, this is more of what we call a deterministic approach. We determine what the vessel type is, what the condition is, and then we put a factor of safety. But working group 211 changes the whole approach. There's more from deterministic approach. We have moved from the deterministic approach into probabilistic approach. It's more bespoke to site condition. It's been developed safety classes similar to the one used in Eurocodes and ASCE 7. I think it's important to note that one of the tasks Working Group 211 has been put to is to make sure that in the last 20 years that the guideline has been used is to sort of get synchronization with more present day guidelines. So the working group members had to go and pretty much understand what the requirements in Eurocode, ASCE 7, just to make sure that we actually cater for all these new changes or these present day changes into 211. Now, we have also used the rational approach of LFRD in partial load factor with the energy instead of force. So that's the approach that we have taken it from. We also included uncertainties in fender performance, multiple fender contact, which is incorporated into the partial safety factor, ensuring consistent targeted levels of safety. Now, partial load factor is based on a 50-year return period with 5,000 berthings, 100 per year. That's the approach we've taken out here as compared to Working Group 33. So different arrival frequency, operational condition does directly impact the load factor. So that gives us a more bespoke design factor for a scenario, and that's what we're trying to achieve. Now, in conclusion, for the partial energy factor, Working Group 211 gives clear guidance on how to apply adjustments to berthing energy factor based on the berthing condition, the variation of vessel sizes, safety classes, and it includes the uncertainties of fender performance, multiple fender contact, and temperature in this partial safety factor. So the end result, Working Group clearer and easier guidelines. Working Group 211 is a lot clearer and easier guidelines to use compared to Working Group 33 because it's more prescriptive. It's more, there's more explanation, tables, conditions provided in 211 itself. Now, the selection of fender system. Now, fender system is, there's a whole table in section 6, figure 6.1, where it actually determined the flow method, the design method from selecting a fender to base performance. When does base performance being called a characteristic performance, and when the design performance is obtained and how it's verified with the applicable fender. I'll go into a bit more details in the next one. Now, application of fender types. There is a table in 211 that talks about different vessel types and different application and the types of fenders. So we start off by giving a designer a bit of an background on what type of fender we can go with, what is perhaps not suitable for the berth or for the application purpose. So there's a bit of a guide to that, which Working Group 33 probably had, but not in the depths that Working Group 211 has gone into. It also talks about site-specific criteria, experience and judgment of the captain bringing the vessel in. Now, base performance versus characteristic performance. I think base performance is pretty much well understood in the industry. It's just the normal formula half mv squared. And that's pretty much what base energy is is based on. We've also applied all the factors of safety in that. And then there's a correction factor which we've got, which is velocity, temperature, and angular. So these factors will be worked out once we get the base energy absorption, multiplied by multiple fender contact if there's multiple fenders. And subsequently, we get what we call as characteristic performance, which we use to go back to manufacturer's catalog and get the appropriate fender types or softness or grade. Vessel hull pressure from berthing impacts. Now, I think in short, there's not been much change in vessel hull pressures. They are pretty much quite the same as 33, but in doing so, the working group understood what the working group met with shipbuilders based in South Korea to understand the characteristic of the build of vessel hull itself. So the transfer of fender loads to structures of the vessel must be done without exceeding the yield stress of the hull plating. So what we had to do is we had to understand the spacing of the stiffness in shipbuilding by talking to naval architects and shipbuilders. So we are very clear on what the hull is capable of taking. So that was then later checked back against the hull pressure table and verified. So all the hull pressures that we've got in working group 33 is currently pretty much close to what the vessel would experience in terms of maximum forces. There's no limit to how much force a hull can resolve, but it depends on the localized area of how much of concentrated force we've put in. So in general, the table that you see on your right here is pretty much the same. So that table at the bottom right is what working group 211 currently holds. Differences in fender sizes between working group 33 and 211. Now, I think this slide here talks about the difference of design approach. If you look at working group 33, you'll see there's a the basic formula of half mv squared doesn't change, it stays the same. Now, the use of factors have changed slightly. We do not have the berth configuration coefficient and softness factor. These numbers are typically used as 1 in the design world unless there's something really specialized. So that has been removed. So 211 only has got added mass and eccentricity of coefficient added into the formulas. Now the approach is the same. Once we work out the energy in 33, the energy is taken and multiplied with a factor of safety, which I provided in the table earlier. But for working group 211, there's an 8-step approach to determine what the probabilistic factor is. And this is where the factors for specific site condition berth gets more bespoke in terms of how it's applied. And it's very important for a designer to use the factor the right way. There are guidance to it, but it's something which as writers of 211, we would like this to be as clear as possible. So please use it and provide your feedback on what differences have you got on your design. Now the adjustment factors then goes back down. Once you've applied the adjustment factors, you compare your energy with the energy that the manufacturer gives us. But for working group 211, there's another factor which we look at if there is a multiple fender contact. So in theory, the approach is the same, but there's just a bit more steps required for 211. Now, this is a comparison of an example project where we took vessel ULCC up to 384 meters with a displacement of 257 plus thousand tons. And we look at 4 scenarios where scenario 1 looked at PIANC working group 211, but with available factors. Scenario 2 is when we went up to the table of favorable and we took a berthing approach based on what the recommendation is. Scenario 3 and 4 is done to Working Group 33. Now, we've applied the site-specific data in Working Group 33 to see what happens to the fender design. And 4 obviously is the stock standard 33 method that we use. So what happens is you can see the velocity row. There's a difference in velocity. What is surprising on this condition over here is if you look at row 4, where you've got the berthing velocity as a lot lower than what the actual velocities are. So what the designers on this berth understood was, if I go with condition C, it should be adequate, but it's wrong because the recorded data ended up being a lot more than what Mr. Brolsma's curve recommended. So berthing velocity for Working Group 211, on the other hand, now 0.15 is a lot more higher than what other velocities are, but because that is a very conservative number in 211. But if you go with the actual data, you can see the actual data points out to the right number. Now, I would like to put a bit of a perspective over here. When I say 0.1, the recorded data, that's an average data. It's not maximum or minimum data. So there's an average block that structure has, which is included into the site data. Now, the next row below, which is factor of safety. Now, factors of safety 1.5, which is taken out as a deterministic factor from 211 stays 1.5, but from 33 stays 1.5, but for 211, now using this, the factors drop. We have actually used the, I missed out this one, yeah. So there's a table on the right there, you see, is how the factors of 1.2 is obtained from 211, where we drop back to class A, moderate condition, and pilot assistance. So we take into consideration of whether the vessel comes in assisted by a pilot, regardless whether there's 10 tugs or 1 tug, but there is pilot assistance. And then there's a variation in displacement as well, which is taken into consideration. That's how the 1.2 is obtained. Now, in comparison, the end value of the fender that we selected, if you look at it, now coincidentally, we've actually got the 211 column 1 and row 1 and row 4 pretty much on the same fender sizing, but the grades are different. So that would mean the reaction force drops a lot smaller. So what I'm trying to say here is the approach that we have taken in the design is very different, but we've ended up somewhere around the same fender size as 233. Now, what's interesting on this one here is for for column number 2, you can see the fender that we have taken with a very, very conservative approach with 211 ended up being heaps bigger, a lot bigger, because we didn't have any site data present. But what I want to point out here is on row 3, when we use the actual site data, what the site should have had under Working Group 33 should have been 1.6. So you can put a perspective into how this calculation was undertaken and the difference of what 211 versus 33 is. Now, I would have really loved to open up my spreadsheet tonight to just give you an idea of how this works and what sort of factors were used. I don't think I've got the time to do it for today, perhaps a talk for another day. All right, testing of fenders. Now, why do we test? Well, make sure manufacturers produce the fenders as per their catalog performance data. Now, what's designed is sometimes not necessarily what you get on site. There are peaks and troughs of reaction force. Sometimes energy absorptions are not adequate and stuff. So it's very, very important that designers spec their specification or get involved with the testing side of it to make sure that whatever fenders that we design on structures comes as it is, so we don't overload the structure. Now, it's also very important to make sure fenders are tested appropriately to verify material quality, performance, and durability. These guidelines suggest what buyers should specify and how suppliers should provide about testing. Now, I've deliberately put in pictures of manufacturing on the site because there is also a chapter in 211 that talks about manufacturing of fenders. I think a lot of engineers, structural engineers like myself, do not get into the details of how a fender is manufactured, but I think it's important for us to understand what component causes what reaction into a fender. For example, if you put in a lot of carbon black, what happens to the fender? If you're putting a lot of synthetic material in a fender, what happens to it? Or if you put in a lot of pure rubber, what happens to it? Obviously, your cost goes up, but what reaction, what sort of longevity we get. And there's a bit of write-up on that on the new guidelines, and I suggest every designer to go and have a read at least once, just to get an idea of what a build of a fender is all about. Now, what's changed in 211? Obviously, we've got 33 had an appendix of testing, an appendix A, I think. But 211 has now taken the appendix and made it into a big section, not a big section, but a prominent section that spells out how fenders need to be tested, under what condition it has to be tested. So 211 has included a new chapter. It includes views of recent research by fender manufacturers in relation to durability and performance. So fender material composition and influence of performance and performance factors. This has changed a lot in the last 10 years. And it's very important that this learning is actually included in a guideline as a fender, PIANC Fender Guidelines for 2024. Now, the impacts of aging is another factor which has been written a lot about in these new guidelines. I think it's quite important to note that a lot of people, a lot of owners, facility owners like to buy spare fenders and keep it in their yard, thinking that one day, if my fender breaks on site, I don't have to buy a new one. I'll just pick it up and I'll chuck it on the berth. But I think that's one criteria which everybody needs to understand, that fender is a material that hardens up over time. And if that's not broken into, please expect 15 to 20% peak in the reaction forces, at least for the first impact. So your structure needs to have a very high factor of safety. So there's guidance given to end users on what do we do with spare fenders. Do we need to rotate them like how we rotate our wheels, the car, front to back, back to front? Or do we need to compress it every now and then? Or what do we do with it? So please, there's a lot of stuff in the guidelines that talks about this. Now, recommendation on testing procedures for fender materials and performance, including representative scope testing, consistency of procedures and compliance of fender testing and facilities, quality control, samples to be tested, how many samples, what do we do with the samples and how they're handled, independent testing and verification. So there's also guidance. There's also a table that provides when or why we need a third party to be present during fender testing, the importance of monitoring it and making sure that the fenders are actually tested compliant with 211. Now, the three types of testing methods provided in 211. There's fundamental type approval, which is pretty much done by the manufacturer to develop the fender curves, the fender values, the catalog values. So it's very important that we put that method in the guidelines. Now, verification testing is when we design a fender and someone buys a fender and we just want to make sure the fender is compliant to what the catalog says. And that's when verification testing is done. So I've highlighted in blue that it needs to be witnessed. Now, manufacturers test conducted by manufacturer needs to be witnessed and verified by a third-party agent or conducted at a third-party lab. It's very important that this requirement needs to make into a lot of our specifications, just to make sure that the fender is QA'd in the right way possible. Otherwise, it's very hard to say if we'll achieve the minimum energy absorption or maximum reaction force. So these are just safety nets which are recommended in the guidelines for a user and a designer. Sorry. Yeah. All right. So this slide here talks about temperature stabilization of fender. So for those of you who are familiar with fender testing, it's similar to a design where when we design, we apply a factor of safety for temperature, velocity factor, and angular factor. So in a control and test environment, a fender is usually tested on a very slow speed compared to the 0.15 meters per second speed that we recommend. So a factor of safety a velocity factor needs to be applied. Now, most fenders are tested perpendicular. There's no angular applied over there. And the third thing is temperature. So temperature is very, very important. So under control condition, now on site, we apply a temperature, a factor for temperature, which is granted because you can't control the environment. But in a test environment, it's what I call controlled environment. Hence, the fender, if it needs to be tested, it needs to be temperature stabilized. So in the previous guidelines, which you see the fonts in red down there, that provides you a formula on how many days a temperature needs to be stabilized. That depends on the rubber thickness of the thicker section on the fender. But this has been revised. Now, the graph on your right, you see here, the dark line is what we got for working group 33. But the lighter lines is what we obtained for working group 211. Now, what you will see the pattern in this graph here is the smaller fenders, which are what I call the typical size fenders, usually takes a lot faster to stabilize. But when we start getting into fender sizing, which is more than 400 mil thick, that's when it gets pretty challenging to stabilize this fender. So this guidelines here talks about how long it needs to be stabilized and tested before that. Now, fender testing. Now, step 2, compression tests. Now, I've actually got this graph over here that pretty much indicate what the reaction force is when it's broken into. And you can actually see it actually, for a new fender, it peaks up to about 30 or 40% of what the reaction force is meant to be. So in a test environment, when you get and you look through the performance curve, always expect a 30 or 40% peak for the first break-in of a fender. And then the second and the third one is what we call stabilizing compression. So that should stabilize, and that can be done after the fender is rested for 5 to 10 minutes on the testing platform. Now, the fourth cycle, typically done after 1 hour or more, to allow the fender to stabilize, because when it's compressed, it generates heat. So it needs to be rested for about an hour. And then the fourth compression is usually what is recorded as the performance of the fender. So these are just guidelines that or methods of testing which has been included in 211. So a designer needs to take the fourth cycle, which is a recorded cycle, for the performance of the fender. That's it. That's it. Thanks a lot for your time.
Thanks, Harvinder. I think you managed very well. When I looked at your 30 odd slides this morning, I was a little concerned whether you'd be able to manage finishing your presentation within 45, but you managed very well. Thank you.
Reminding myself to speed up things. Sorry if I rushed.
Okay, I think we can open the floor for the questions. If you have any questions, let me know. I was told by my IT that I'll get a call from my director of operations if I drop this mic down. So I'll come with the mic around if you have any questions.
Thanks, Harry. Jim Hutchison from WGA. I mean, I'm really interested to understand that comment about berthing velocity. Currents have no impact on berthing velocity.
Yep.
That's very different to my experience in navigation simulation with pilots and the like. So I'm really intrigued to understand more about that compared to, cross currents versus longitudinal currents.
Yeah.
So how does that How do you come to that conclusion?
Well, it's the findings in 211 came from working group 145. So 145 has determined that there's no environmental consideration in berthing approaches or velocities, very operational based. So we've taken that findings and incorporated into 211. So perhaps there's a table that talks about currents in 211, which provides you some direction. If you're concerned of current flows, especially in a river berth, then it's probably something which can be considered as a factor. But in my experience, current flow is quite impactful to mooring assessment more than berthing. And on that point, since we're talking about mooring, there's also guidance on moored vessel and the influence of fender fatigue. So that's something which is also covered in this guideline. Sorry if I don't answer your question, but I think it's something which we have incorporated, but came from 145.
Thanks. Yeah, Chris Millwood from Specialist Sport Equipment. So I've just got a question on areas in the work group look at combining the group of vessels at the port. So, for instance, the coefficient of variation of mass, and also, the section on multiple fender contact. My instinct would have always been to break up each individual vessel and look at each individual vessel based on the number of berthings to which coefficient of variation of mass would have little effect. Yet your number of berthings in the design period would. So what's your comment? Should designers look at the group of vessels at the berth or break down vessels individually when designing?
The probabilistic factor does cover for group of vessel, multiple vessel approach. So there is a factor which influences your probabilistic based on a variable type of vessel sizes, vessel approaches, how often vessels are berthed, and when it comes in as well. So it's all operational based. Yeah, does that answer your question, Chris? Yeah, that's a good point, Chris. There are some vessels that will come in once or twice a year, but there are some vessels that come in every other day. So, yeah, I think in that case, the factors of safety in the probabilistic table does have a recommendation to drop these factors based on an average number. So you've got a table with two different numbers. What I would do is I would take the average number based on the size of the vessel and then tweak the factor based on that. Does that answer your question? Correct. Just on that point, we're also looking at I think there's a version on our SharePoint for Working Group 211 on trying to update some of these tweaks or some of these questions that we get. I'll put that through with the working group, but in 2026, there will be a revision coming up. There are a couple of typos here and there that needs to also be fixed on the document.
Thanks, Harvinder. I'm Ravi Segu from KPI. Of course, you know me. On the comparative example between WG211 and 33 regarding berthing velocities, the example actually has 0.15 for the ULCC and then 0.095 for 33. Particularly for where there is no site-specific data is available. So do you think for greenfield terminals where no data available, the fender sizes will go up comparatively when compared to WG33?
Well, that's a very interesting question, Ravi.
Across all the vessels, I mean, this is of course one vessel, but do you think for other vessels classes also will be the similar comparison that we can expect? Because I can see between 1800 and 1400 cone fender, maybe 50% material gone up on the rubber.
Correct. I think the probabilistic approach is very data driven. So the short answer to it is yes, if you don't have data, then you need to look at the worst case scenario. But having said that, you might be able to get data from the adjacent berth somewhere nearby that can be applied into your perspective. So if you're looking at a greenfield project, there's a high chance if you go with 211, you'll end up getting huge fenders. And as your design matures and more data comes to light, then there will be a optimization of the design. I don't think there's a short way of trying to use unless you know what the approach of vessel within a certain district or certain port precinct, then feel free to use those figures.
Yeah, I was wondering 0.15 meters per second for a 257,000 DWT class vessel seems to be definitely a conservative number.
Yeah.
But is there a basis actually in choosing those numbers?
Yes, it's
there is no data.
There's a table that has got favorable, moderate, and unfavorable. So each of this column has got a classification or more of an explanation on when we pick favorable, unfavorable, or moderate. So based on your criteria, you'll end up getting one of these columns. So that's usually what we do. Now, I'm not suggesting we do this, but a very experienced engineers will pick an average number between two columns sometimes. But again, it's not advised. Well, when you don't have a data, it's a greenfield job. You just need to go with the recommendation that 211 gives. So the message here is data collection. We're in an age where data is pretty valuable, and that's where it comes in handy with this guideline.
Yeah, thank you, Harvinder, for an interesting talk. The probabilistic approach velocity chart that you had in 211 that you had on the screen, does that include equipment failures? The reason I ask is I was actually on a ship that had an equipment failure, slammed into a wharf, folded up the wharf and put a hole in the ship. And that was the main cause.
Sorry, which graph, Peter? Can you just refer back to me? Was it? Hull pressure? Well, the berthing approach or the velocity that we look at does take into account of worst case scenario in terms of what Ravi was talking about a short while ago. It's high, but it caters for the worst case scenario. So I've been in a situation where a client has come to me and said, all right, a vessel berths a structure at a considerably slow and light ship condition. So the displacement is quite light. But then we fill the vessel up and it gets filled up. But then it needs to depart. It's not going to berth back. But the client has come back and said, look here, we need to put this criteria in which we call rebirth. Just in case of an emergency, the vessel needs to come back into the berth. Even if it moves for a meter, comes back again, then that's fully laden vessel. So that scenario is what we looked at. If that's going to be a worst case scenario, a design needs to be done for a worst case scenario when data is not present. Yeah.
Yes, the equipment.
All right.
Is that addressed somewhere in this?
That's not addressed, Peter. That's a very, very specialized condition. But yes, it's something which you can have a think about. But it's usually not standard operation at a port. But unless if it's requested for, then that's something which a designer should look at a bit out of the box. Yep, it's insurance. That's it.
Yeah, before we go to the other questions from in-person attendees, there are a few questions from the online attendees. I can't see the full name, but one of the questions is, thanks for the presentation. WG211 focuses on local data being available, but many port owners, operators won't have local velocity records, particularly the smaller or more humble facilities. The second question is, how significant is the effect of the lower berthing angles on the berthing energy?
Well, I answered the first question first. Yes, I think we need to condition ourselves to talking to port owners, asset owners, to get data. I do understand some ports, some very regional area ports, don't have the capacity to put in gauges or sensors to monitor velocities. I think that's probably where the worst case scenarios apply. It's a condition where I think, if a vessel comes in without unmonitored, uncontrolled, will slam into the structure. Now, the concern here is not only the structure, but also the hull of the vessel. It needs to be catered for in the design. So I don't think we have covered for regional ports or regional areas where we can't collect data. Now, the second question with regards to the berthing angle, there is a table. I don't have it on screen. I've got it in my manual over here if anybody wants to have a look. There is a table in here which talks about definition of berth approach. When is it considered a parallel berth and when is it considered a angular berth? So this is for those projects where there's no definition of approach vessel. So in that table, we discuss things like whether it's tug assisted, what sort of conditions we're looking at, operational condition when the vessel comes in and stuff. So there's a definition, there's a guidance to berth angle on that table. Now, in terms of the significance to the design, yes, there is a significance of approach angle to your energy calcs. It does affect the whiplash effect of the vessel when it touches the berth. And that's something which has been accounted for in our calculation or design.
But also, from manufacturers, there are some tables based on the berthing angle, what correction factor
Correct.
could be applied.
Yep. There are some guidance in there as well. Correct.
So there is another question from online attendee. Thank you for the presentation. Your fender selection example talked about the berthing velocity was averaged to be 0.1 meters per second. Some were higher and lower. Should it be 50-year EP to match the safety factors, or it's the average of, or is the average sufficient?
It should be 50-year EP for the working group 33, but 211 uses a different EP for the design calcs in terms of what the velocities are. So that is different to what data we have. If there's present of data, then the data is used. Otherwise, just go with the 0.15, which is quite high. Yeah.
Hi, Harvinder, Chris Lehman from KBR. I guess this goes back to the importance of the data collection. So is that something you see most clients having? Like, would you expect most clients to have that data? And what would be involved in collecting that data? I assume, you need more measurements than one berth event. So how long would you need to collect data to inform the fender selection?
That's a very good question, Chris. I concur with you. There's not many ports in Australia and New Zealand that currently collects data, but it's something which I think we need to, as engineers or as designers, we just need to encourage port owners to start looking at data collection, because it can literally result in a more optimized design, because we rely on a set of data. That example which I provided, I'll show you. Let me just go back to this example which I provided over here. If you look at row number 4, that's based straight out of working group 33. Look at the velocity, and that's compared to actual velocity. So had we not collected actual velocity, I think the fenders are a bit under designed in my opinion. So that's the significance of getting data out. Now, the second part to your question is, how do we do it? I think this is probably well, it's probably for someone to develop outside there to develop sensors or a mechanism to collect. I know there's some suppliers have got sensors fixed on their fender panel, some on the structure which senses the vessel approach, and data is collected into a cloud space. But that's obviously for the likes of big ports, international ports around. But I think someone needs to look at a cheaper option, more feasible option for smaller ports or regional ports. But it's a space where it needs to be improved in the industry.
I'll take a couple of more questions from online attendees. Hi, Harvinder. Thanks for the great presentation. As most wharf tenants have no clue about fender maintenance and service life of the fenders, does WG211 provide some insight on this?
Yes, that's a good question. I've not covered it in my presentation today, but Working Group 211 document does cover maintenance, installation, and also what do we dispose? How do we be sustainable and dispose these fenders? Can we recycle it? What sort of uses can a fender go? Because very often we put a fender on a berth, we keep it there for 30, 40, 50 years, whatever the duration of the service life is. But then we take it as just chuck it in somewhere in the backyard, which you don't know what to do. Well, interestingly, I actually bought a second-hand fender because I love fenders from airport in Singapore. It's a SCN 300, and it's something which I do always every morning look at it before I start my work if I work from home. Well, call it a way of recycling. Just got it as a showpiece at the back. So anyone talk to me from my home, you'll actually see the fender at the back of me. So well, that's just that's me. But there are ways in 211 that talks about how can we sustainably pull it out. Now, I think during the working group meetings, the Netherlands, if I'm not mistaken, are looking at a project where fender is crushed and used in kids' playground as a platform, a recycled platform, because you can crush fender into a smaller one pieces, and there's a glue that's been put and flattened out with heat, and it's working pretty well. So that's one way of doing it. However, we can't implement that here in Australia. It's quite costly when it comes to the processing of taking a fender and using it. I've also seen fenders being put in the sea where it's been used as coral breeding ground for corals and all that fish habitats and stuff like that. So there are a few ways of trying to do it, some of which is covered in 211.
Then, thank you for the presentation. I have one question. Does fenders design or governed by the moored vessel motions at the berth? Because in moored analysis, we focus on fender reaction safety.
Correct. There is a section that talks about how fender is related to mooring analysis. When a mooring analysis needs to consider the reaction from fender force, partial contacts of fender panel to vessel, because very often some vessels, multiple size of vessels, some vessels partially contact because of flare angles, stuff like that. So there is some guidance on that. I'm sorry, I don't know right on top of my head what it is, but I do recall one of my working group colleagues talking about it and including it in the guidelines. So the answer is yes, but I can't give you a straight answer for it now.
Great. So yeah, we are 3 minutes over. If there are any questions from the floor, this would be the last one. Yeah.
To make it a good one then. Harvinder, I guarantee you everyone in this room at some point in the next 2 decades will come against a project where the structure's designed for a certain class of fender. And now we're going to need to look to, or we're going to be looking at fender replacements or something similar. How would you propose we deal with that situation, noting that Working Group 211 is planned on taking over in 2 years? I mean, is it we do a risk-based approach, we calculate it in accordance with Working Group 211, say the guidelines based on that's impractical, therefore we stick with the existing fender and test it to Working Group 33 superseded standards, or what's the recommended approach?
Grant, I think when I said update in 2 years' time, it's not every 2 years, but it's just currently we are in a transition period between 33 and 22. So 33 is still left in place because manufacturers need to develop their catalog to suit 211. So we've not got to that point where we could integrate everybody straight across to 211. But the updates that we're talking about is minor typos, minor errors that has been picked up by quite a few people in the document. You can expect it's quite a bulky document. It's been about 27 hours who had a sort of share of, had a go into the document writing in different sections. So there are areas that needs to be fixed, but I don't expect it to be a major overhaul of the document in 2 years' time. It would be a minor update. Now, if I understood your question right, you're talking about existing facilities, which is currently designed to working group 33. If you've got to assess it to 211, what happens to it? Now, that's a very interesting one, Grant, because this question has came up numerous times. Now, what I would say is, before you do that, the first question you ask your port owner is, do you have data? Because if you have got data, I don't think you're going to end up coming with a bigger fender unless your operational requirements have changed at the berth, then that will influence your fender sizing, definitely. So for now, those who wish to use 33, please use 33. I'm working on a project that's currently using working group 33. And those clients who have got data and are happy to integrate into to working group 211, I think that's a very good approach. I'm encouraging a lot of people to go to 211. To answer your question, Grant. Thanks. Good.
Harvinder, I have one question, but considering we are 5 minutes over, I'll leave that or I'll ask you in the networking session. Thanks, Harvinder. One more time, and we have some food and drinks here. Help yourself. Thank you.
Thank you. You're welcome. Thanks for coming.
Thank you.